Alright guys, I know you can't wait to be rid of me, but one more week and that will happen. Alright, so in Laplace transforms we talked about the bilateral, which is the standard one we discussed, and the unilateral. So something similar exists for Z transforms as well. And again, just like in Laplace transforms, the goal of using the one-sided transforms is to solve difference equations similar to differential equations in continuous time. So again, to distinguish from the usual Z transform, I'm going to try and use this curly X. I'll try my best artwork, but make sure you don't confuse it with the straight X. All right, and then the big difference is that the sum now goes from 0 to infinity rather than going from negative infinity to infinity. That's the only difference. Everything else is the same. So you have x of n, z to the negative n. That simply means you're taking x of 0, adding x1 times z inverse plus x2 times z to the negative 2, etc., right? If the signal has something before time 0, like x of negative 1, x of negative 2, too bad. They just don't get representation in the unilateral Z transform. All right, so a lot of the properties of the standard Z transform carry over to unilateral, but some don't. This is very similar to the unilateral Laplace transform. Can you remember what did not work for unilateral Laplace that worked for the usual Laplace? Differentiation was slightly different. Good point. There was one more. Convolution. So essentially there is no convolution property of unilateral Z transforms, because when you take convolution of signals, it's likely to extend to both ends, right? Why would we think that it should start at 0? So convolution will not work unless you know that the two signals for which you're taking convolution start at n0. But at that point, the unilateral transform is the same as the bilateral, so it's just the usual property of the bilateral transform. So x1 convolution with x2 of n will give us a unilateral Z transform, uz for unilateral, that is the product of x1 of z times x2 of z if this is a big if, x1 of n is equal to 0 for all n negative, and also x2. So I'm just going to say xi of n, I1 and 2. Okay? So that means really there's no convolution property of the unilateral Z transform, unless it happens to be the same as the Z transform, right? All right. So that's fair, because we don't, convolution is useful for LTI systems. For LTI systems, we have 0 initial conditions. So the purpose of unilateral Z transforms is not to deal with LTI systems to derive transfer functions and things of that sort. It's not that. The goal is to solve difference equations with given initial conditions that are not 0. Okay? So therefore, we don't really care if convolution works or not, because we're not interested in analyzing LTI systems with unilateral transforms. What we're interested in is solving difference equations, and for those we will need initial conditions. So that's the other property that's different. That's the time delay property. Slightly different than the usual Z transform. So the difference is this. If I give you an x of n, signal x of n, whose unilateral Z transform is x of z, and then if I delay this signal by 1, meaning I shift it to the right by 1 time unit, it has some similarity to the usual property of the Z transform. What would that be if it was the standard Z transform? Z inverse, right? Remember, Z inverse is delay. Z inverse is delay. That's important. We'll see Z inverse a lot, and remember that that just means delay, shift by 1 unit. So there's that, but there's an additional component now. So far, this looks like the usual Z transform property of delay. The difference is this. So if I take my signal, shift it to the right, x of -1, which was ignored by the Z transform before, by the unilateral Z transform, is now at time equal to 0. So all of a sudden it appears and has to be accounted for in the unilateral transform. So that's why we have this addition here of x of -1. Clearly x of -1 was not part of x of z, that x of z being the unilateral transform. But now that it's shifted to the right, it's within the window that affects the Z transform, so it should be added. So more specifically, the proof of this goes as follows. So when we are looking at the unilateral Z transform of x of n minus 1, we're looking at the sum from 0 to infinity of x of n minus 1 times z to the negative n. So if I write this out explicitly, for n equal to 0, I have x of -1 times z to the 0, which is 1. For n equal to 1, I have x0 times z inverse. For n equal to 2, I have x of 1 times z to the negative 2, and so on. So this part looks almost like the usual one-sided Z transform if you look at the equation at the very top, except that it has a factor of Z inverse. So if I factor out Z inverse, that simply looks like what I have at the top, right? So that's therefore equal to that, right? And that's why this property follows. The proof is one line, simple. So we can apply this property repeatedly. So, and then we can derive an expression, for example, for x of n minus 2. X of n minus 2 means you took x of n minus 1 and shifted it by 1 more, right? So therefore, it's going to be z inverse times the z transform of x of n minus 1, which is what we have from this expression we just derived, right? X of z plus x of -1. But in addition, I need to add the value of x of n minus 1 at n equal to 0. No, at n equal to -1 to be consistent with this formula here, right? And that is going to give me x of -2. So if you simplify, you're going to have z to the -2 x of z plus z inverse x of -1 plus x of -2. All right? So this part is identical to what we had for Z transforms. Delay by 2 units would multiply it by Z to the -2. But now we have these additional terms that are due to the initial conditions. Right? So you can see how that would be generalized. If it was n minus 3, then you would have z to the -3. You would have z to the -2 multiplying x of -1, z to the -1 multiplying x of -2, and x of -3 appearing by itself. And you can generalize. All right? So the time delay property is crucial for solving difference equations with given initial conditions. So let's see how that works with an example. So solving difference equations, just like we solve differential equations with unilateral Laplace transforms. This time we're in discrete time, so we're solving difference equations with unilateral Z transform. And I will only work out an example here because you guys are smart enough that you would know how to generalize that. So the example is this, very simple. First order difference equation. Subject to initial conditions. So we are solving it for n equal to 0 and more and higher, but we are given an initial condition. So here's our example. Standard form difference equation. 0.6 y of n minus 1 equals the forcing term, x of n in this case, is 0.5 to the n times the step. That means before time equal to 0, nothing is happening. At time equal to 0, the input kicks in and we're solving the difference equation. This is a first order difference equation because there's only one delay element involved. And for a first order difference equation, you need one initial condition to solve it. And that means we need, since we are starting to solve at 0, we should be given y of negative 1. Okay, so I'm going to leave it symbolically, so we'll assume y of negative 1 is a number that's given to us. Okay, so let's see now how the z transform, the unilateral z transform, helps us solve this difference equation. So take the unilateral z transform of both sides of the equation. So this gives us, I don't know how to make a curly y, I'll try something weird, okay? And minus 0.6 times the unilateral z transform of y of n minus 1. And what is that again? Z inverse y of z plus a correction term. What was it? Y of negative 1. And that's where the initial condition comes into play, right? And then you take the unilateral z transform of the right-hand side, which is the same as the z transform of the right-hand side because that starts at n equal to 0 due to the unit step. And you should, of course, all know what that is. What's the z transform of the right-hand side? 1 over 0.5 z inverse, right? So that comes from the general a to the n times u of n Laplace transforms we had discussed earlier. Okay, so we are close. So let's put all terms that contain y of z in one expression. So that will give us 1 minus 0.6 z inverse times y of z. And then let's put everything else on the right-hand side. So what is left here is 0.6 times y of negative 1 and the z transform of 0.5 to the n. Okay? So the right-hand side, of course, can be simplified. You would have to multiply this denominator with 0.6 y minus 1. And that should give you what? It should give you 1 plus 0.6 y of negative 1. Then the product of negative 0.5 z inverse with 0.6, so that should be 0.3 y negative 1 z inverse. That's what goes in the numerator. And then there's a denominator, which is 1 minus 0.5 z inverse. All right? So we're almost done. So y of z, I can obtain that by dividing both sides with 1 minus 0.6 z inverse. So you get all the terms you need. Again, I did not give you y of negative 1. It was not specified. We do it symbolically, leave it alone, and try to get a result that depends on y of negative 1. So the role of the initial condition is explicit. All right, so that is what I have. 1 minus 0.6 z inverse, 1 minus 0.5 z inverse. Okay, so what do I do? when I have an expression like this and when I want to find the inverse Z transform. Partial fraction is useful, so we try to write it in this form. Some number A by 1 minus 0.6 the inverse plus another number B 1 minus 0.5 Z inverse. And then we match the coefficients of the numerator, and that's how it goes. So you've been exposed to that before, so I don't need to work that out, but I can give you the result and you'll probably believe me. So if you solve, if you match the two sides of the equation and solve for A and B, A happens to be 6 plus 0.6 y of negative 1, which depends on the initial condition. And B, interestingly, does not depend on the initial condition, and it is negative 5. All right? So from that, we can figure out what the solution is. So y of n is just the inverse Z transform. We're going to get a right-sided signal, so the unilateral and bilateral coincide in this case. Okay, so I'm going to first write A n minus 1. Okay, so what does that give me if I do the inverse Z transform on 1 over 1 minus 0.6 Z inverse? 0.6 to the n times U of n, right? All right, and then corresponding to B, negative 5, we get .5 to the n U of n, right? Just looking at the expression, d by 1 over 0.5 Z inverse, okay? So that's the solution, you got it. Nobody's complained, that's not n, of course. The whole problem was to solve this difference equation, so it only depends on the initial condition, right? All right, so we did it. Now, it was simple because it was only a first-order difference equation, but you get the idea from this. All right? So, in some other coursework, you may have seen other ways to solve difference equations like this. Perhaps. Eigenvalue decomposition, if you did 16, which in this case is scalar, so it's already decomposed, or the standard way of doing homogeneous and particular solutions, right? So don't worry about it if you've never seen this before, but the most usual way that any undergraduate course on this matter would teach you is if you're given a difference equation like this, where is it? Y of n minus 0.6 y of n minus 1 equals 0.5 to the n for given, we're solving this for n greater than or equal to 0, and y of negative 1 is given. All right? The usual way is to find a homogeneous solution. Homogeneous means imagine that there is no forcing, there is no 0.5 to the n. Okay, so just find a solution that makes the left-hand side equal to 0. So h of n, 0.6, h for homogeneous, right? So solve this equation, right? So from the very structure of this, you can postulate a solution of this form. Because of this 0.6 here, you can postulate something like a times 0.6 to the n. Okay? Because if I take that and find yh of n minus 1, that's just a times 0.6 n minus 1, right? And yes, okay. And if I take if I take yh, so if I substitute these two back in here, put this here and put that here, what do you get? You get a 0.6 to the n minus 0.6 times the other term, yhn minus 1, which is this, right? So that's just, because 0.6 is multiplying this, together they'll give you 0.6 to the n, so it will cancel and it will be 0, right? So that's the homogeneous solution. No matter what a I select, that is going to make the left-hand side of the equation equal to 0, right? So that's one piece of the solution. The other piece, the important piece, is the particular solution. For a difference equation of this form, you basically look for a solution that looks just like the forcing function. Some coefficient times 0.5 to power n. And ask yourself, what should B be so that the difference equation actually works with this particular solution? It's a solution that works, right? So if I substitute this back in here, yp of n minus 0.6 yp of n minus 1 is b 0.5 to the n minus 0.6 b 0.5 n minus 1. And that is, everything has a b in it, right? And everything has 0.5 to the n. But I'm going to factor out 1 minus 0.6 times 0.5. And what is that? 0.7? So you get 0.7. Something tells me this is wrong. Say it again. No, I think you're right. Yeah. No, I think you're right. No, because something's wrong here. I want to, okay. So if I factor out 0.5 to the n out of 0.5 to the n minus 1, what remains is 2, right? Not 0.5, 1 over 0.5. Do you agree? Okay, so this should have been 2. My bad. Okay, so that gives us negative 0.2b, all right, times 0.5 to the n. That's what I get on the left-hand side if I substitute b times 0.5 to the n. That has to match the right-hand side, which is just 0.5 to the n with no factor. So those cancel, and b should be negative 5. All right? So there you go. We found the particular solution. That is negative 5.5 to the n. So what do we do when we find the homogeneous and particular solution? We add them up. So the general solution y of n is a times 0.6 to the n minus b, which we know has to be negative 5 times 0.5 to the n. Okay, so sum of the particular and homogeneous solutions. Now, if I substitute this back in the equation, the first term makes the left-hand side equal to 0, right? No matter what a is, the first term makes the left-hand side equal to 0. And the second term makes the left-hand side equal to the right-hand side. So therefore, any solution of this form works. But not any solution of this form satisfies the initial condition. Okay? So therefore, we solve for a. A is an indeterminate variable at this point. We solve for a by matching our solution to the initial condition. Okay? So y of negative 1. So basically substitute y of negative 1 in this expression to solve for a. Okay, so that is the end result if you use the classical approach. But let's compare this solution to what we found using the unilateral Z transform. Really the same thing, right? So we had a times 0.6 to the n and minus 5.5 to the n. So naturally it gives you the same thing. The fact that B did not depend on the initial condition kind of makes sense because we know from the general structure of the solutions of difference equations that that was the particular solution. That was part of the solution that was driven by the forcing function 0.5 to the end. Okay, and it makes sense that that term does not depend on the initial condition. Okay, so that's basically an alternative to the classical method. And I'm not going to do anything else with unilateral transforms. Again, the thing to keep in mind is that this is not for LTI system analysis. It's for solving difference equations with given initial conditions. Okay? When we deal with LTI systems, there is an implicit assumption that the initial conditions are 0, in which case we don't need any of this. We just use the bilateral Z transforms. And then the convolution property and everything else that matters for LTI systems works. All right. Do you have any questions? If not, this is it for unilateral. Yes, no, going once, going twice. Okay. Back, here. One more. All right. Are you done? So the next thing we'll talk about is interconnections of discrete time LTI systems. And here there's nothing really new for you guys because everything we saw for Laplace transforms and transfer functions for continuous time systems is the same idea. So, but let's, as a way to review those discussions from earlier, let's just talk about this. So let's say that, so this is interconnections of discrete time LTI systems. Oh, by the way, did you get the homework? Homework 6? Due Friday, right? Now it's optional, but that doesn't mean you shouldn't worry about it. I mean, it's part of the exam, therefore it makes a lot of sense to solve optional homework problems, right? And we'll, give the solutions, but do it on your own first, right? So otherwise, what's the point? All right, but anyway, back to our discussion. So if I have the series connection of two discrete time systems, H1 of n, and the output of that drives another LTI system whose impulse response is H2 of n. All right, and comes the output. So this is X of n, this is Y of n. The intermediate signal here is X convolution H2 of n. But the nice thing about Z transforms is that, you forget about all of this. Convolutions go away. So this becomes X of Z. This becomes H1 of Z, the transfer function of the first. This becomes H2 of Z. And then Y of Z is the product H2 of Z times H1 of Z times X of Z, right? And so this piece here, the product of H1 and H2, is the transfer function of the interconnection. So if you have a series interconnection of two LTI systems, you just multiply their transfer functions, and it's as simple as that. If you have a parallel interconnection, you add them up. So this time I'm not going to write explicitly the impulse responses. I'll just put the transfer functions, H1 of Z and H2 of Z. And to get the output, I am going to add up their individual outputs. So this is a summing junction, and what comes out is Y of n. All right, so clearly Y of Z in this case is H1 times X of z plus h2 of z times x of z. So you just add the two up. h1 of z plus h2 of z x of z. And that means the sum of the two transfer functions is the transfer function for this parallel interconnection. The third one, which is slightly more interesting, but we saw it before, so it won't be that interesting after all, is the feedback interconnection, where let's say we have h1 of z in the feed forward, and that gives us y of n at the output, and then a negative feedback with h2 of z in the feedback loop. All right, so who remembers y of z in this case? This is very easy to derive anyway, but so if you ever forget this formula, don't despair, just do it from scratch, but it's better to remember anyway. So it has this form, all right? So it is important to note that this works when we have a negative feedback. So that negative results in a positive here. If it were to be a positive feedback, this would have been a negative. Right? So let me put this with a different color. So if this were to be positive, this would have been negative. And the derivation of that we did before, and I'm not going to repeat it. Let's instead talk about an example. And here is my example. So let's say we have this form. X of n comes in, and there's a branching point, and we apply a delay to it. So we're going to be seeing a lot of block diagrams in the rest of this lecture, so this is a good start for that. So we delayed it once, and we delay it one more time. And that's what we get, right? So what we'll do is we'll add a summing junction here. I guess I'm not being super consistent about summing junctions. Sometimes I put a plus. If you see a circle, just assume that it's a summing junction, okay? All right. And instead of putting blocks, let's just do a shortcut. So I could say, I'm multiplying this by B0, okay? Okay, so B multiplied by B0, a coefficient. So when it's a coefficient, we'll just take it easy and not draw a box. I'll just do this instead, and you will know what I mean. So I will just put an arrow, a conspicuous one, and put a B0 on top. That means whatever came into that arrow got multiplied by B0. Okay, does that make sense? So this signal at the junction, it gets multiplied by B0 by the time it reaches the summing junction. Well, is that clear? Okay. So I'm going to do the same thing here. And this is going to get multiplied by B1. And then this is going to be multiplied by B2. And nothing to add here. I'm just going to take this signal, feed it to the top. And then I'll sum these up and feed it here. And together, all of them summed will give me y of n. Okay? So what on earth did this block diagram do to my signal x? So what is y of z in terms of x of z? Or what is the transfer function of the whole block from x to y? So that's the question, right? So with a repeated application of some of these series parallel things we discussed, we can actually figure out the transfer function for this block diagram. So let's first concentrate on this part. This box here. With input here, so this is what's coming in, and output this. That's not good. Anyway. All right, so can you tell me what transfer function I would get for that orange block? Orange block is basically a parallel interconnection of two branches, right? One has gain B1, the other has gain B2 as well as a delay. So when we have parallel interconnections, what do? We just add the transfer functions, right? So this first branch here has transfer function B1, just a constant. And the second branch has gain B2 as well as delay. Okay? Yes? Agree? All right, so now that I can actually just collapse that orange block into a single block, right? It's just some block with this transfer function. Forget what's inside. You already characterized its input-output behavior with a transfer function. So you can minimize it if you had the chance to click on it and get rid of it, right? So it's just a box, and I know how it behaves, right? I don't need to know what's in it. Okay, so now let's think about what remains. So the rest is easy, right? Because now I have B0 in one branch, and then that branch splits, gets multiplied by Z inverse, goes into this box that we already characterized, B1 plus B2 Z inverse. And then that gets added here, and this is Y of n. And this is X of n, right? So what's the overall transfer function? In other words, what's the transfer function for this new bigger box? Again, you have two branches in parallel, correct? So what are their transfer functions? I will add them up. The upper branch is just B0. And the lower branch is a series interconnection of two things, so I multiply them. Right, so Z inverse times B1 plus B2 Z inverse. All right, all together you have B0 plus B1 Z inverse plus B2 Z to the negative 2. All right, so that's the transfer function. Make sense? Okay. Any questions? All right, so if you look at this, there are no feedback loops here. Do you agree? We never had to use that feedback rule, right? We only use the first two rules, the series and parallel interconnections. Because things are branching out and then feeding back in, but not backwards. So it's all feed forward. Things flow forward from the left to right. Nothing flew backwards. So let's now look at another example where actually there is feedback. So this was all feed forward structure. So another example with feedback. So in this one, I have X of n coming in to a summing junction now. And then the output of that sum basically gives us Y of n. Okay? But then we take that Y of n, delay it by 1 unit in time, and delay it again. So we have two delay elements. Okay? And what happens is we do another sum here. So that goes up. And so we are going to multiply this guy, the delayed y, with negative a1. And then we are going to multiply this one with negative a2. And I want to know what is the transfer function from x to y. So can you propose any strategies? The goal is to use those three simple rules we discussed: series, parallel, feedback interconnections. With a combination of those three, perhaps we will not even need all three, we should be able to find the transfer function of the whole thing. So like we did in the previous example, we can actually study this block here. So we can first characterize that and move it out of the way. Okay, so the input to it is this, and the output is this, right? So what is the transfer function there? What kind of interconnection is it? It's parallel. The first branch is just a constant gain, negative A1. The second branch is negative A2 times the inverse. That was series, so we just multiplied the gain with the delay. Okay, so with that, the remaining interconnection, now that if we minimize that orange box into a single transfer function, what remains is simple. It is just that orange box, YFN at the output. There's a Z inverse, and its output. Oh, this is not a great drawing, but you can live with it, I guess. So, and then this box, right? Okay. So as it is, this looks like positive feedback, and what's inside the block is negative A1, negative A2 Z inverse. But that's the same as, removing these negative signs here and making that negative feedback. Same idea, right? So what is the formula then for the overall transfer function? Remember the rule for feedback? Whatever is in the forward branch goes in the numerator, right? And in the denominator I get 1 plus the product of the two things, but that's if we have negative feedback. So because this is positive, I'm going to put a minus instead, okay? And that means I have the product of Z inverse times negative A1, negative A2 Z inverse. Okay, so these negatives can be replaced, because if I put a positive here, these become positive as well. So what's the answer? 1 over 1 plus A1 Z inverse plus A2 Z to the negative 2. Okay? So now let's call this example 2. This is example 2. And let's go back and call this example 1. So look at example 1. We created B0 plus B1 Z inverse plus B2 Z to the negative 2. And then we have the second example. So using these two, if I ask you to find an implementation, some realization for this transfer function, B0 plus B1 Z inverse plus B2 Z to the negative 2 by 1 plus A1 Z inverse plus A2 Z to the negative 2. Okay? So what is now I'm asking you, what is a block diagram that will give me this transfer function? Looking at the results of examples 1 and 2. So let's look at this. So let's call this h2 of z, because that was example 2, right? 2 for example 2. And that basically gives us the denominator of what we want to build, right? And in example 1, we have h1 equal to this, and that's the numerator of what we want to build, right? So essentially, what I'm trying to build here is h1 of z, which is the numerator from example 1, times h2 of z, which is the term we have from example 2, right? So therefore, I'm really trying to build a system whose transfer function is a product of those two. So what kind of interconnection does that mean? It's a series interconnection. So what I could do is I could take this block diagram, okay, take its output, feed it to this guy as the input, and their combination would be an implementation of that second order transfer function we discussed. So I'm going to show you a tidier picture instead. So it's basically this. Just came like that. I wasn't expecting it to pop up the right spot, the right figure. Okay, so the blue block here is the result of example 1. Actually, there is something more going on here. Example 1 stopped after 2 delay elements, right? Whereas this one keeps going. All right, and this one, the orange one is like example 2, but again, we have more than 2 delays, right? So if you were to just guess, what transfer function would you predict for this? So this is h2 of z. We know what this was when we had only 2 delay elements. And it was 1 over 1 plus a1 z inverse plus a2 z to the negative 2. So if I had a third one with a feedback term a3, negative a3, what do you think would add to this? a3 z to the negative 3, etc. Right? Okay, so just the structure suggests that. You can actually work it out and find out for yourself. And then if you look at the other one, that's a generalization of example 1, this one. This one is actually easy. So it's going to be b0 plus b1 z inverse plus b2 z to the negative 2. And if it keeps going, then you would have to add b3 z to the negative 3, etc. Right? So therefore, with this series interconnection of these two, you get h of z, which is the product of h1 of z with h2 of z, which has the general form of a transfer function we discussed before. You know, our typical transfer function of this form can be implemented with this block diagram. So this basically suggests a computational structure, right? So each of these Z inverse blocks are delay elements, so they are memory registers, right? So this is telling us how we can build the computational architecture to do the filtering, right? Feed in an input X to get a Y that gets modified according to this transfer function. You would have to build this computational structure. All right, so now when you look at this, does that look familiar, this transfer function? When did we see it in that form? So when we discussed how to go from difference equations to transfer functions, that's exactly what we saw, right? The difference equation then was this: y of n minus a1, y of n minus 1, minus a2, y of n minus 2, etc. equals b0 times x of n plus b1 x of n minus 1 plus b2 x of n minus 2, and if you want, this can go further. b2 x of n minus 2, etc., right? If it continues. So that's from last lecture, from last week this time. So we saw that if we have a difference equation like this, the transfer function will look like what we have at the top. Okay? So therefore, this block diagram shouldn't surprise you at all, because that block diagram is basically describing, forget about the transfer function, just focus on the block diagram, and keep in mind that z inverse means delay, right? So then you should be able to see that this difference equation is nothing but a description of what's happening in the block diagram, or vice versa. Block diagram is showing us with a picture what this difference equation is doing, right? Because y of n is this output here, and what happens after it's multiplied by z inverse in time domain? Z inverse means delay, right? So this becomes y of n minus 1. And this is y of n minus 2, right? So if you focus on this summing junction here, this is telling you that y of n is this signal, don't worry about it for now, just this signal, minus a1 z inverse and a2 times z to the negative 2, right? And basically, this summing junction is giving us all these terms here. Okay? Now, where is this arrow hidden in the equations? What is this arrow anyway? It's the sum of b0 x of n plus b1 times x of n minus 1, right? And this is x of n minus 2. So the right-hand side is really this. Okay? So all of the equation is, therefore, what this equality says in the difference equation is just happening here. It's equating y of n to the sum of these negative feedback terms plus all the input terms that's flowing in this branch. All right? So in a sense, this block diagram is easier to connect to the difference equation, but we know that both of them also connect to this transfer function. So everything is connected with everything else. All right, good point for a 5-minute break, and then we will continue from here. Oh, so that's where you go. You get lunch. I don't know. Is there anything nearby? Oh, I see. Okay. Now I know at the end of the semester. Okay. That's right. Okay, that means we can start. Okay, so a simple question here about this block diagram. Okay, so now we agree that you can implement this transfer function here with this block diagram, right? But there is a cost to every block diagram in terms of memory registers. How much stuff do you have to register to memory in doing the computations, right? How much memory do you have to use? So that you can judge by the number of the Z-inverse elements here, the memory registers that are needed, right? So in this expression, in this block diagram, it's M plus N, M being the degree of the denominator because the orange block will have M of those delay elements. And then you will have N of them in the blue one. I'm sorry, M in the blue because that's the numerator, and N in the orange, which is the denominator, right? Okay, so can we do better than that? Can we have fewer delay elements, in other words, memory elements, so that we can do computations with in a less memory intensive way, right? So a simple idea comes to mind, actually two steps. First, this is the product of numerator and 1 over the denominator, h1 of z times h2 of z. So if I switch the order of those two, does the transfer function change? That's a property of LTI systems, right? Take two LTI systems, swap their order, you're doing the same thing. So that means I can do this, right? What I did here is I just swapped the orange and the blue. It used to be that blue came first and then it fed into the orange. Now we changed the order, but it's still the same transfer function. Do you agree? All right, now looking at this carefully, do you see a way to economize a little bit on the delays? Yeah, so these two signals here and here are the same. You're delaying the same signal, okay? You're allocating memory to remember what that signal was twice, and then doing the same thing for this one and so on, right? So there is no reason to have two separate memory registers there. You can just merge them into one, right? So that's basically what happens here. You can just merge them, and it's still the same transfer function. Only you have fewer delay elements, fewer Z-inverse elements, and you'll get the same transfer function. How many? Can you guess? The maximum of M and N. If both have the same length, if their depth is the same, then you remove all duplication and merge, half the number of registers, right? But then one could be longer than the other, then, that determines how many we need. All right, so in general, so that you would need maximum of M and N Z-inverse elements versus M plus N, which was what was needed before we swapped the two. Okay, so that's good to keep in mind. All right, so now that we're talking about transfer functions and how to get transfer functions, let's talk a little about state equations for discrete time systems. So state equations for discrete time LTI systems. We talked a little about those for continuous time LTI systems. So the idea is similar. So we're going to have a state vector. I'm going to call it W and put this arrow on top of it to indicate that it's actually a vector. And it's going to be a function of time. But now we're in discrete time. So it was x of I think we called it back then, we called it z of t for continuous time systems, right? Z is unfortunate because now we're doing z transforms, so too many z's around. So I'm going to switch to another letter from the end of the alphabet. That's not z, which W will do. So that's our state vector. Okay? So the state equations for a linear time invariant system are going to have this form. The state at the next time instant is equal to a matrix A times the state vector at time n. Okay, so to advance from time n to n plus 1, you're taking the state vector, multiplying it with a square matrix A. A is square, and its dimension is the same as the dimension of the vector. If the vector is m dimensional, this is then m by m. And then the input enters through a vector B, and we assume the input is a scalar. All right, so, and then the output is related to the state variables as well as to the input. So y of n is given by a row vector C times Wn. So this row vector is going to have the same dimension of W, so that's really an inner product. Row times column, it will give you a scalar. And D is a scalar times x of n is also a scalar, so you get a scalar y of n. Okay? So these are the state equations. Compared to the continuous time state equations where we had d by dt of z of t equals a z of t plus bx of t, and y of t equals c z of t plus dx of t. So a similar idea. We're just advancing in time rather than taking the derivatives, right? So the question is, what is the z transform? I mean, what is the transfer function of an LTI system given by these state equations? So what is the transfer function? TF4 transfer function. Okay, so what should we do to get the transfer function? We can take the z transform of both sides of these equations, both of them, right? So let's do that. So z, everything you see, z transform. So what happens to the left-hand side of the equation, w of n plus 1? If capital W denotes the z transform of little w, I'm going to put a vector here again. All that this means is, remember, little w is a vector. So big W means take the z transform of every entry in little w and put them again, stack them into a vector, call it big W, right? So, okay, so, but then if it's advanced in time by 1 unit, what does that mean? Multiply by z, so that's the time shift property, right? When we delay the signal by 1, we multiply by z inverse. When we advance the signal by 1, we multiply it by z. Okay, so z transform of both sides of both equations. All right, so what's on the right-hand side? By the linearity of z transforms, this is just a times w of z plus b times x of z. And y of z is, again by linearity, c times w of z plus d times x of z. So here we'll use nothing but the linearity property. Okay? So the goal here, what does a transfer function do? A transfer function relates the input x to the output y. So there are too many variables here. We want to eliminate the state variable. These are intermediate variables. We want to get rid of them, so we get an expression for output versus input. How do I eliminate w, though? Well, when I see W's, I can combine them into one. So this equation simply says Z minus A. But remember, Z is a scalar. A is a matrix. So to make them compatible, you write Zi minus A W of Z is equal to B X of Z. And that implies that W of Z is Zi minus A inverse B X of Z. And what you do is you take this expression, put it in here, and that will give you C times that times X of Z, and plus D times X of Z, so they all get added up, times X of Z. So what we are seeing here is the transfer function H of Z. Does that look familiar? When we took the Laplace transforms of the continuous time state equations, the transfer function had the same exact form. It was C times Si minus A inverse B plus D. So really it's the same formula, just S becomes Z. All right, so that's convenient, one less thing to remember. All right, so just to summarize, H of Z is C Zi minus A inverse B plus D. Now when you invert Zi minus A, you'll get the characteristic polynomial of A in the denominator. And that characteristic polynomial will be a polynomial in Z, right? So that means the denominator of H of Z, so denominator of this, I can never write these things, denominator of H of Z is the characteristic polynomial of A. When does the characteristic polynomial vanish? When the variable Z is an eigenvalue, right? When does the denominator vanish? When Z is a pole. That means poles of H of Z are the eigenvalues of H of Z. Again, we had made a similar observation for continuous time case. Are E values of A. All right. All right, so now that we know this connection, this is important. Again, it's the same as H of S for continuous time state models. Now that we know this, it's convenient to go back to some of the examples we discussed for interconnections. Right? We had these three rules, we mixed them up, we combined them, and we were able to obtain transfer functions for an interconnection, say, of this form, or an interconnection of this form, right? Well, it turns out all of these are, the derivation of a transfer function from a block diagram is a lot easier if you use a state representation as an intermediate step. Maybe this was the more complex example, right? So if this was a longer chain, then I would have to do this repeatedly, apply the feedback rule, etc. It's a mess, algebraic mess, right? It requires some ingenuity about how you break it into individual steps, right? Instead, if you see a generic block diagram, rather than try to see how you can apply the simpler rules for series, parallel, or feedback interconnections, forget about all these interconnections, just write a state equation for this. Okay? Try to represent everything in terms of a state model for a block diagram. And from that, you can use this formula here to go to a transfer function. Okay? So what I'm suggesting is when you have a block diagram, going directly to a transfer function can be cumbersome. You may be able to do it at, we were able to succeed in those examples, right? But, it's not very systematic. Okay? So it's a cumbersome procedure. Instead, what you can do is write state equations for the block diagram, and we'll talk about how to do that in a second. And then now that you have the state equations, it's easy to go to the transfer function using this formula above, right? From the state equations, you know A, B, C, and D. And then you apply this formula and you get the transfer function. Okay? So the only thing we need to know, we know how this arrow works. We know how to go from state equations to transfer functions. We just need to know how to go from block diagrams to state equations, and that's actually fun. It's really fun. I mean, it's like a little puzzle, but there is a procedure for it, and it follows very nicely. So I will illustrate that procedure on an example, and that example will be the same example we had on our notes. So I'll just take this structure. Just forget where it came from. I somehow know what that's actually implementing, but let's erase our memory, and suppose we don't know what transfer function goes with this. And let's try to get a transfer function by first writing state equations for this block diagram. So, and we'll keep it simpler by stopping at 2 delays. Okay? So we're going to have, I'll just illustrate basically what I'm doing here is I'm illustrating how to go from block diagrams to state equations on that example. And the procedure is general and can be generalized to an example. In fact, you have a homework which is a slightly different example. You should definitely do it whether you're turning it in or not. All right, so this is our system. One delay here, and then it splits into 2. Negative A1 goes here. B1 goes here. One more delay. And then again splits into 2. B2 goes to the right. Negative A2 goes to the left. And that feeds here. This will go up and add to this. And this will add to that. And it will give us Y of n. Okay, this is our parsimonious realization or implementation of the second order transfer function we discussed, but again, let's pretend we don't know that. So what we'll try to do is we'll try to get the transfer function here by first writing state equations. The one thing that you should do, and that always works for any example, not just this, is to select the state variables as the outputs of the delay elements. If you do that, the rest is very easy. Okay, so don't just define random state variables. Just however many delay elements you have, you should have as many state variables. And you should select the state variables to be what flows out of these delay elements. Okay, so I'm going to call this W1 of n, my first state variable, and this W2 of n. Okay, so that's step 1. Step 1 is to label outputs of delays as state variables. And basically we've done this for this example. Okay, that's the simplest step. All right, outputs of delays become state variables, and then things become easy. Step 2, now we want to write the state equations. Remember, state equation is something like W1 of n plus 1 equals such and such, right? And W2 of n plus 1 equals such and such in terms of the states, right? So how do I find out what those are? Do you have any suggestions looking at the block diagram? How can I get an expression for W1 of n plus 1 and W2 of n plus 1? Where is W1 of n plus 1 in the block diagram? Well, if I labeled the output as W1, W1 of n plus 1 is the input to the delay. Right? That's all there is to know. So I get ahead of myself. Okay, so therefore W1 of n plus 1 is really this signal here. The input to the delay, that way the output of the delay is W1 of n. Similarly, the input to this is W2 of n plus 1. Is that clear? If it's not clear, I need not talk any further. If it's clear, I still don't need not talk any clear because the rest is trivial. Okay, makes sense? All right. You want me to write it out? Okay, so step 1 said label outputs of delays as state variables. Step 2 says, okay, let me find a way. So write state equations. Equations using inputs of the delays because they give you Wi of n plus 1, right? But how do I know what that's equal to? Well, I have to look at the interconnection, the structure of the block diagram. The block diagram is going to come into play somewhere, right? And this is where it comes into play. Step 2 is where it all happens. Okay, so you just have to write the equation for W1, looking at the other state variables. Okay, so write state using inputs of delays. Express each. In the notes, these are written somewhat clearly anyway, but so express each as a weighted sum, as a weighted sum of states and input. In other words, when I write the right-hand side here,
Vishnu and Jesus Christ share two things in common.
You're having a class, I'm sorry.
And they're both the same. Kalki is away.
This happens. We're in Berkeley. We're in Berkeley. It's a daily occurrence. At least he had clothes on. Okay, so let's concentrate. So I want to write W1 of n plus 1, right? And I want to express this in terms of nothing but x and the other w's at time n. N plus 1 is not allowed, just n, right? Why? Because I'm going to have to bring that to these equations to this form here, right? And there, the right-hand sides depend only on n, right? So we're not going to depend on n plus 1. Okay, so what is W1 of n plus 1 in terms of x, W1, and W2? Well, this answer is in this. For W1, the answer is in this summing junction, right? Because the output of that summing junction is W1 of n plus 1. And the input is the sum of three things. What are those? There's an x of n, yes. I'm going to put that last. It takes care of this one, right? And then there's this component, which is what? Of n. And then there's this one, and the two add up here, right? Come here. So that is negative A2 W2 of n, right? Okay, so mission accomplished. Now W2 of n plus 1 is this signal here, and how can I relate it to W, the other W's and X? It's actually trivial in that case. It's just W1, right? So it's just W1 of n. So done, we have our state equation, right? I can put it in this form because eventually I'm going to need A and B. So I can just write it in this form, W2 n plus 1, the vector form that is. W1 of n. So that 2 by 2 matrix in the middle is going to be our A matrix. And then we're going to have a 2 by 1 times x of n, right? So that's our A. This is our A, and this is our B. Let's fill them in using the equations we already derived. We're just putting it in matrix form. We're not doing anything new here. We're just packaging what we already have. So what goes in A? Minus A1, minus A2. So we took care of these two. And now let's take care of this x. What do I do to take care of x? I put a 1 here, right? So first equation is done. Second equation is simple. I just need to create W1, and I do that by putting a 1 here, 0 here, and 0 here. So we're done with our A and B matrices. Okay? So what do you think step 3 would be? Now that I have my A and B, so what else do I need to be able to use this formula? I have A, I have B. Well, I need C and D. Where do C and D come from? They come from the output equations. The output needs to be related to the states and the input. So step 3 does just that. Step 3, write output y of n in terms of x of n and the state variables, w1 of n to all the state variables, right? And that will give you to obtain C and D. And once you have C and D, you're done. So if we try to do this for our example, we can. So let's do it. Okay, so maybe I'll try to work it out in this corner. So a little step 3 corner here. Step 3. So I want to write y of n, right? So what is y of n in terms of the states and input? Y of n comes from the addition of 3 things, right? So this one, which itself is the addition of these 2 things, right? So y of n is B1 W1 of n, right? That takes care of this. And then B2 W2 of n, that takes care of that. We're almost done, although what remains is this part. And that needs a little more work because that signal, the additional signal coming in, is W1 of n plus 1. And that's not good enough. You want the right-hand side to be clean. Just needs to depend on x and w at time n. N plus 1 is not allowed, right? So I will have to substitute this here so I can eliminate w1 of n plus 1 and be able to write everything in terms of states and input at n, not n plus 1. All right, but that's not so hard. Oh, and also, no, I think it's fine. Yeah, I think that's fine. Something is fishy. Ah, okay, what is fishy? I'm missing something here in the block diagram. We had a B0, right? Where did B0 go? So it's here. Okay, so this was actually B0 times that. Okay? All right, but we can do it. So just multiply everything here by B0. So that will give us B0, negative B0 A1 W1 of n minus B0 A2 W2 of n plus B0 times x of n, right? And then I have these additional terms. Hiding here, this is B1 W1 of n, and this is going to add to this B2 W2 of n. So if I clean up everything, then I'm going to get y of n in this example. B1 minus A1 B0 W1 of n plus B2 minus A2 B0 W2 of n plus B0 times x of n. All right? So what I want to do is I want to write this as a row vector C times the state vector W1 of n, W2 of n. That will give me C. And then something times x of n. And that will be D. So this will be C. This will be D. D is clear. D is just that, right? So B0 goes here. So what are the entries of C? It's this and that, right? B1 minus A1 B0 and B2 minus A2 B0. Okay? Now you know your ABCDs. You can plug them in here. C Zi minus A inverse B plus D, and you get the transfer function. I'm not going to do this. I could, but you know, it's tedious. But the answer, guess, is what? Anyone wants to take a guess? Oh, we knew the answer. That's how we started this example. So it's going to be B0 plus B1 Z inverse. Do this as an exercise. That's kind of useful. B2 Z2 negative 2 by 1 plus A1 Z inverse plus A2 Z2 negative 2. All right. Done. I mean, not quite done. We stepped this several steps, but, you know, do this as an exercise. Okay? All right. So that part is just algebra. That's why, you know, I'm not going to go through it. It is more important, perhaps, to get practice doing this on a different block diagram. So I'm going to give you one. It's actually an easier one where you can actually do these calculations. Not only is it easy to write A, B, C, D, but it's also easy to invert Zi minus A. So I'm going to give you that as an in-class exercise, just so you get some, you know, exposure to how you go through these three steps. Let's see. I could potentially... Cool. Okay. So I have a page in the notes that goes through these three steps. So we can look at that while you do this. Okay. Here is the block diagram. X of n. Some of the gains I will leave them as, you know, symbols, and you will see why I left them as symbols, because the overall transfer function will have a nice structure in it. So a constant alpha 0, not to be confused with the A coefficients of the denominator, not that, so something different. Okay, so that goes to the output, but the output has other things going in it too. So there's another branch. So x gets multiplied by alpha 1. And then there's a little small, oh no, positive. So again, if you don't see a negative sign and the circle, that means you're just adding, okay? Z inverse we have negative d1 here, and this feeds into that, all right? And one more, this one has gain alpha 2, z inverse, no, it's a d1 in the, this is d, and d2, and that goes in here. So the problem is find the transfer function for this, y of z by x of z, in terms of alpha 0, alpha 1, alpha 2, and d1, d2. So it should depend on these 5 parameters, right? And you're going to follow the procedure that we discussed. So what I'm going to do here is, this should be enough time for people watching on the webcast. So I want to show you the procedure just so you, I mean, you can start if you took notes. But I'm going to make a copy of this on the board so we can switch to what's on the slides. Alpha 2. Okay, now we have it on the board, so I can switch to the notes. Here's the procedure. Okay, so you have a different block diagram, but the steps are the same. So work it out. I'll put somebody on the spot to give me the answer. All right, I'm going to start doing it myself. I'm doing step 1. So, n plus 1 All right, so do you all agree with the equations that I wrote? Did you get things similar? All right, so let's put these in vector form. And I told you that was simple because I gave you things that will come in a diagonal form. You probably noticed that. So you know I'm being nice to you. I'm not sure about the exam. Maybe I won't be that nice. Okay, so something times the input, x of n, right? So the entries are negative d1, 0, and alpha 1. So that takes care of this. And then 0, negative d2, alpha 2, that takes care of this. And then y of n, one and 1, right, for these two, plus alpha 0 times x of n. So this is my A, this is my C, this is my B, and this is my D. All right? So because A is diagonal, Zi minus A inverse is easy. First of all, Zi minus A is Z plus D1 and Z plus D2. And the inverse of that is 1 over Z plus D1 and 1 over Z plus D2. Okay? And then what you're going to do is you'll multiply this from the left by C and from the right by alpha 1 and alpha 2. And what do you think that gives you? You probably did this already. All right. Okay, that's it. So h of z is alpha 1 over z plus d1 plus alpha 2 by z plus d2 plus alpha 0. There you go. So that's the answer. You can simplify more, but that's the idea. All right, so let's stop here, and we'll see you on Wednesday. Enjoy the last week of class.